show you a little bit about how we are observing Comet Kohoutek. The panel that we have right in front of me here is the Apollo telescope mount control and display panel, and we're using the instruments which are controlled through this panel for observing the comet. These instruments were originally designed for studying the sun, and we still do use it extensively for that purpose. But we've also found that some of these instruments are quite capable of learning quite a bit about the comet, and I'll try to discuss a little of that for you today. I think we've been rather fortunate that Comet Kohoutek was picked up and discovered quite early so that we could get a good observing program put together to study it. Another exceptional thing about the comet is that it's coming relatively close to the sun, or it has been already, and therefore is heated, becomes quite bright, and we hope in that way show us quite a bit about how comets are made and how they change. It's just gone through a relatively dynamic period. On December 28th, it came within 250,000 miles of the sun, which is really quite close, and it was traveling at a speed of about 250,000 miles an hour. Now it will tend to slow down as it moves away from the sun, and also tend to decrease in brightness. However, as it does get a little further away from the sun, you folks down there will be able to see it and be able to enjoy the same spectacular sight that we have been up here. We've been quite lucky. We have 15 nights, transitions into nights and days up here for every 24 hours, so we're able to see it quite frequently. An advantage for us being up here is that we're above the Earth's atmosphere. That allows us to see it without any of the intense light scattering that exists within the Earth's atmosphere. And as soon as it comes above the horizon, we can see it and observe it. We've used quite a few of the onboard instruments to do that. And first, let's talk about the ATM. In general, what we try to do is to take a picture of the comet, same as you would take a picture with any camera you would have at home. We also, at the same time, try to learn a little bit about what colors that the comet really emits. By colors now, we mean not just the ones you can see with your eye, but those all the way down into X-rays. We don't expect X-rays, but we do expect some ultraviolet emission. Surprisingly enough, there's very little real hard data on comets, even though they've been noted since almost 500 BC. We hope we can make a significant step in that direction, along with some of the other observing programs which are being carried out at this time. We'd like to know whether it's made of ice, rock, whether there's methane in it, complicated molecules, whether it's hydrogen. Numerous questions which will tell us a little bit about where it came from and perhaps how the solar system was put together. We've been able to do a fairly extensive observing program, despite the fact that we have only or have lost one control moment gyro for maneuvering. We started out with 3 and have lost 1, which we felt was a significant impact, but fortunately the people at Houston have gotten very smart, worked hard, and figured out some fairly good ways of getting the job done with the reduced capability. The first instrument, and perhaps the primary one, for the purposes of finding the comet and pointing to it, is the white light coronagraph. That's controlled through this section of the panel here. And we use these two TV monitors to find the comet by using the instrument in conjunction with a TV camera that has mounted into it, which gives us a picture of what the instrument sees. Since the corona, that's the atmosphere around the sun, is relatively faint, and the comet is also, the instruments are pretty well matched. However, as you go in towards the center of the sun, the corona gets very bright. The coronagraph here has taken that into account and filtered out most of the light very close to the sun, so that only the edges of the field of view, if you will, the regions right around here, are capable of seeing the comet. Once we move it in close to the center, we can no longer see it. That means that we have to resort to something a little less accurate than pointing directly at it by eye, and that is we use an overlay grid pattern here, if you will. We find out where the comet is, and then we figure out what its coordinates are on here, and then we figure where we want to move it to, and make the appropriate entries into the computer. Those entries are all calculated from the grid overlay, which we've put on the display, and have had to calibrate just for that purpose. As a matter of fact, right at this moment, the white light coronagraph is observing the comet. And at this moment, I do have to get 3 single exposures going, and then a series of what we call a fast scan. I'll cut off the television for a bit, and I'll be right back with you. We're now looking at the display for the white light coronagraph, and down in the lower left is a very faint object, which turns out to be the comet. The coronagraph was designed to look at the sun, and the corona, which is fairly bright, and the comet being relatively faint just barely shows, but it's still well enough to do the pointing. What I will do now is to make a few entries into the computer, which will move that very small bright point over to another position, which will make our observations. Okay, the entries are now made, and you can see it moving off to a new location. Now you see it disappear. Reason for that is as it gets in closer to the center of the display, the filtering of the instrument tends to filter out the light much more greatly as you move in closer to the center. Okay, we're back with the white light coronagraph in a little different mode of observation now. You can see by the light here, which tells me that we are operating. We hope that the coronagraph will tell us a little bit about whether the tail behind the comet is made of gas or dust, or what combination there is. We're able to make that same separation in observing the corona itself, and we hope we could do the same with the comet. We also hope that there'll be some interaction, if you will, between the corona, that's the region again around the sun and the solar wind which emanates from that, and the comet as it passes through it. I think we'll learn quite a bit about both of them by observing that interaction. Now, a second instrument, which not just takes pictures, but it also gives us some information about the color, and that is, we call it the XUV spectrograph, extreme ultraviolet, and spectrograph means just a way of taking a picture in various colors. In this case, the colors are in the ultraviolet, or extreme ultraviolet. There was a period of around 8 hours when the comet came closest to the sun as we looked at it, that we were able to use this instrument, and I'm full of anticipation that we've got some pretty good data. We'll know when we develop it upon returning home. We're looking for pictures of the comet in emission lines of helium, maybe some of oxygen, hydrogen, especially helium and ionized helium. That is, helium has lost one electron. One of the most useful for determining what the comet is made of is the XUV slit spectrograph, and that essentially, although it does not take a picture, it takes a very narrow slice, if you will. It looks at something about like this pencil, only it's only 1 arc minute long. That's 1/60th of a degree, and about 1/30th of that length in width. So it's just a very narrow slit, but it takes that light and divides it up into all of its colors, all of its components in the ultraviolet, and in that way tells us what are the atoms and what are some of the molecules, if they show up in that wavelength range, which compose the comet, and the tail, and the coma, which is the region around the nucleus. This instrument is an exceptionally capable instrument in terms of what we call